Okay, one of the uses of dimensional analysis is to check for the correctness of a physical equation such as the one we have here. This equation reads S is equals to UT plus half AT squared, where S is equal to distance, U is equal to initial velocity, then T is time, A is acceleration. Okay, so to check for the correctness of this equation, we want to check whether dimensionally all what we have on the left side will be the same as the one we have on the right. We're not talking about the numerical values now, just the dimensions only. So the dimension of distance is L, so that will be equal to the dimension of velocity is LT minus 1, then the dimension of T is T, that's the dimension of time, plus half the dimension of acceleration is LT minus 2, and the dimension of time is T then squared. So if you look at this, you're going to have L is equal to L, then you have this is T raised to power minus 1. If you apply the law of indices plus 1, but this is the same as T raised to power 1 plus half L T raised to power minus 2. Then when you are multiplying that, you apply the law of indices, this is plus 2. So you see that this will cancel, that's 0, and this will cancel out this, that's also what? 0. So from here, you can see that L is equal to LT raised to power 0 plus half LT raised to power 0 also. Now you know any T raised to power 0 is 1. So from here we can say that L is equals to L times 1 plus half L times 1. When you work that, this is going to be L is equal to L plus half L. So you can see that on both sides, the only physical quantities that are present are length, and length. So this is dimensionally what? So we can say that it is dimensionally what? Correct. Correct. Okay, we can actually take some examples at what respective values of x, y, and z will the unit of force Newton be dimensionally equivalent to m raised to power s, l raised to power y, t raised to power z. So what we simply do is to do this force is equal to m raised to power x, l raised to power y, and t raised to power z. All you have to do is to look for the dimension of one force. So we know that you can use the formula to look for the dimension of force. You know that force is equal to mass times acceleration, and the dimension of mass is m. Then the dimension of acceleration is LT minus 2. You can refer to the video, the table on the previous video. So we'll have this one. On this side, we're going to have m LT minus 2 is equal to m to the power of x, L to y, and t to z. So what you just do is to equate each term to each other. Okay, so let me equate m. So this is the same as m raised to power 1 plus m raised to power x. By applying law of this will cancel out this, so x is equal to 1. Then we can also apply that L and L squared. So have L raised to power 1, because this is the same as L raised to power, is equal to L raised to power y. This will cancel out this, so y is equal to 1. Then for t squared, we have t squared is equal to t raised to power z. So this will cancel out this. So therefore z is equal to 1. So these are the values of x, y, and z. So what I just did is was to look for the dimension of f, start looking for the dimension of s, equate it to this side, and equate each like terms to each other. Okay, here's another example. At what respective values of a, b, and c would the unit of impulse be dimensionally equivalent to m is to the power of a, l to the power of b, t to the power of c? So here we're going to write impulse. The symbol for impulse is I. Is equal to, then we'll have this. Then we're going to write this here, m to the power of a, l to the power of b, and t to the power of c. So impulse is simply force times time. So we know the dimension of force to be m l t minus 2 times, we know the dimension of time to be t. If you cannot get this, you can actually start by looking for the formula from force. F is equals to ma, and we know that m is capital letter M and a is lt minus 2. So you see, when you multiply this and this together, this will be reduced to m l t, that's minus 2 plus 1, that's equal to minus 1. So this dimension of impulse, we are coming to this place and write m l t minus 1 equals m to the power of a, l to the power of b, t to the power of c. So again, we'll collect like terms on both left and right hand side. So this is m raised to power 1 equals m raised to power a. So this will cancel out this. A is equal to 1. Then we'll go for L. So we have L raised to power 1. What we'll have here is equals to L raised to power B. And this will cancel out this. So B is equal to 1. And finally, we'll go for T raised to power minus 1 is equals to T raised to power C. So this will cancel out this. C is equal to 1. So the values of A is 1 and B is 1 and C is minus 1. Okay. We can also use dimensional analysis to determine the units or dimension of unknown constants. For example, in this example 2, a sphere of radius r moving through a fluid of density rho with velocity v experiences a retarding force F given by F is equals to K r raised to power A, rho raised to power B, v raised to power C, where K is a non-dimensional coefficient or constant. Use the method of dimension to find the values of A, B, and C. So here we are given that F force is equals to K r raised to power A, sigma raised to power B, and V raised to power C. So we are going to write the dimension of force. We already know what dimension of that's M L T minus 2 equals K. K is dimensionless, remember. Then arrow is the radius. Since arrow is radius is the same as length, so we replace that with A. And rho is density. Sigma rather is density from where it was defined as. So density is equal to mass over volume. And we already know that mass is given as this, and the dimension of volume is L raised to power. So this is the dimension of volume, density rather. So we have times m L raised to power minus 3 all raised to power B times V is velocity, and the dimension of velocity is LT minus 1. You can look up to the table. This smaller dimension, you need to know you need to know them off heart. Okay, so that will be LT minus 1 raised to power C. So we are going to expand all of this now. Okay, so on the left hand side, we have M L T minus 2. Your M should be capital letter equals K L raised to power A. So when I expand the bracket, you're going to be using a lot of the laws of indices. So I'm going to have, so when I expand this 2 to this power, I'm going to have times M raised to power B L raised to power minus 3b by applying the laws of it. Remember that for the laws of indices, a raised to power ab raised to power c is the same as a raised to power c, b raised to power c, or a raised to power b squared raised to power, let's say m, will be the same as a raised to power m, b raised to power 2m. So I'm just basically applying the laws of indices there. So times, so apply that to this again. We have L to the power of c, t raised to power minus, and c multiplied that's minus c. So the next we'll have to do is to collect all the terms, the like terms together. So on that time, I'm going to have mlt minus 2 is equal to k. So the terms in L, so we have this. So that's L raised to power a. So since we are multiplying this by this term here, we can apply the law of indices. Remember that a raised to power m times a raised to power n is the same as a raised to power m plus n. If it is a raised to power m times a raised to power n times a raised to power q, it becomes a raised to power m plus n plus q. So we apply all of this. So this is multiplying this. We have, since it's minus 3, I have minus 3b, okay, times, so we go to m. So I have m raised to power b. We only have that here. And the other side, we only have one c here. That's t here. So that's t raised to power minus c. Okay, so the next thing we'll have to do, is to equate terms on both the left hand side and the right hand side. This is a dimensional constant, so we don't need that. So let's start with m. From here, this will be m raised to power 1 equals, so m here is what? M raised to power b. So this will cancel out this. B is equal to what? 1. It is good to only start with the terms that are alone on this side. So this has a minus b. You see it, a minus 3b. Okay, I think I omitted this here because there's also L here, that's plus c. So this L is going to carry all of this plus c, because of this c that is here. Okay, I omitted that, so there's L there. Then we'll go to the next one. We can now go to L. So on this side, we have L raised to power 1 is equal to this, L raised to power a minus 3b plus c. So this will cancel out this. For me, you can see that a minus 3b plus c is equal to 1. We already have the value for b, but we don't have the value for c and a. So we can just leave that. Then we'll go to the next one. So the next one will be c and d. So from this, you see that t raised to power minus 2 is equals to t raised to power minus c. This will cancel out this. Minus 2 is equal to minus c. Minus will cancel out minus c is equal to what? 2. So we can now come back to this and find the value of a. So we have a minus 3. The value of b we calculated was 1 plus c is 2 is equal to 1. Okay. So from here, you can say that a is equal to a minus 3 plus 2 is equal to 1. So I have a minus 3 plus 1 is minus 1 equals 1. From here, we can say that a is equal to, if this goes this way, becomes 1 plus 1, which is equal to 2. So therefore, a is equal to 2, b is equal to 1, and c is equal to 2.